Hello everyone and welcome back. In this video we're going to talk about the behavior of functions and how some important terminology can help us give some nice or good descriptions for our functions that'll set them apart from each other. Here are 4 terms that we may have seen or even used before, but that we're going to define in this video and give some examples of. And here are a couple of graphs that are going to help us illustrate these features or terms. So we're going to talk about what it means to be increasing, decreasing, concave up, and concave down. So some of these terms we probably are familiar with, like increasing and decreasing, maybe informally, but let's go ahead and start there. So informally, if we say a function is increasing on some interval, then that just means the function is going to be going up as we move from left to right on that interval. And on the other hand, decreasing means the function is going to be going down as we move from left to right across that interval. So if we look at these 2 functions we have graphed here, we can see that the first function is increasing throughout its entire domain, and our second function is decreasing throughout its entire domain. Notice how both of these functions have the exact same domain and range of all real numbers, so having some other type of descriptors, like where it's increasing, decreasing, concave up, and concave down, can really help us distinguish these 2 functions and set them apart. So we have our informal definition for increasing or decreasing. We go up or down as we move from left to right. We want a more formal and algebraic statement for that as well. So we're supposing the function we are describing here is our function y equals f of x, and a function is increasing if f of b is greater than f of a, then that implies that that x value of b, or that input value of b, must be larger than the input value of a. This is just our algebraic or symbolic way of saying what we said earlier. As we move from left to right, as our x values get bigger, that's moving from left to right, our outputs have to also get bigger in the same way. That's exactly what these little inequalities are saying. Another way to interpret our symbolic statement for increasing is this is saying if our outputs are getting bigger, so f of b is bigger than f of a, then that means b must be bigger than a. The corresponding inputs must be getting bigger as well. So we're increasing if as the inputs get bigger, the outputs get bigger as well. While for decreasing, the opposite is occurring. The outputs should be getting smaller as the inputs get bigger. So if the outputs are getting smaller, that is f of b is less than f of a, as long as b is greater than a, then our function will be decreasing on this interval where this occurs. So in green, we have our more formal statements or descriptions of what it means for a function to be increasing or decreasing on some interval of x values, including a and b. And in pink, I'm just providing our informal explanation or definition of these concepts. Up next, I want to talk about concavity, and this might be a new set of terminology for some of us. So let's go ahead and start with the informal description of concavity, and then we'll go ahead and formalize it. So we say a graph is concave up if we think of that curve or visualize that curve as being bent upwards. While we are concave down on an interval where our function or the curve for our function is bent downwards. And so what I mean by this, by bending upwards or downwards, is think about taking a straight line. It doesn't really matter how you orient it, but if we had a straight line here and we wanted to bend our straight line into this piece of our graph, if we had a straight line, would we have to bend it downwards or bend it upwards to obtain that shape? Well, if we have to bend it upwards, then that shape is concave up for that piece. And if we have to bend it downwards to create that shape, then that's going to be a concave down piece of our graph. So you can see in our first function, this first piece is concave up until we hit about x equals 0. And then we switch to being concave down. Well, for our second graph down here, it starts as concave up for that first piece, and then it switches to becoming concave down. Some really important shapes to remember to keep this idea of concavity together are just 2 parabolas. right? So here we have like y equals positive x squared, and here we have y equals negative x squared. I really like these examples for concave up and concave down because they really encapsulate all the different types of scenarios. One thing that people kind of have trouble with initially is thinking if a function is concave down, it has to also be decreasing, and if a function is concave up, it has to also be increasing. That is not true. We can have any combination of increasing or decreasing with either type of concavity. And that's what we can see by remembering this concave up parabola or this concave down parabola. For this entire upward pointing parabola, we are concave up. On the first half, we are decreasing though, and on the second half, we are increasing. So this little bit is what a decreasing concave up graph might look like, while this other bit, the bit to the right, is going to be an increasing concave up graph. Down here, we have something similar going on for the other possibilities. Throughout this entire graph, we are concave down. On the first piece though, we are increasing since we are going up, and on the second piece, we are decreasing. So you can see we can be increasing in concave down, or also we could be decreasing and concave down. That informal definition of concavity should get us through this class, but we're still going to go ahead and write down the formal statements of being concave up and concave down on some interval, because we're going to need them eventually. And so the more formal definition of being concave up or concave down on some interval is we say a function is concave up on some interval of x values if on that interval of x values, the rate of change of the function is increasing. It's not that the function is increasing, but the rate of change of that function is itself increasing. On the other hand, for downwards concavity, we say that a function is concave down on some interval of x values if the rate of change decreases throughout that interval of x values. So we will revisit these concepts in calculus and get into a lot more of those details in that class. But I do want to try to clarify what I mean by the rate of change increasing or the rate of change decreasing. The rate of change we are most familiar with and have spent the most time working with is the rate of change of a linear function or the slope of a line. If the slope is positive, then that line or that function is increasing. And if the slope is negative, then that line or that function is decreasing. And so what we're describing here with concavity is really how that rate of change or how that slope is changing. So if we are concave up, then our slope or rate of change is going to be increasing. And so if we think about that, maybe here on our parabola, at the vertex of our parabola, this little bottom part, it's like the flat part of our parabola. If we had a little line there to approximate or represent our parabola at that spot, it would probably be a horizontal line. But as we move further to the right, we can see some kind of line that would approximate our parabola, would have a slope that is actually getting steeper and steeper in the positive direction. So we can see as we move throughout this curve, the slopes of these lines are getting more and more positive. The slopes or the rate of changes are therefore increasing. And that happens over here as well, where we're still concave up, but it's just going from a negative number to a positive number. So it's still increasing, maybe just a little bit harder to visualize that. And the exact same thing is going to happen wherever we are concave down or bent downwards, right? Maybe we can start over on this side where our function is increasing, so it has a positive rate of change. But what happens as we move throughout this interval? Well, the function stops increasing, it starts decreasing. That rate of change is decreasing, as we can see from the slopes of these approximating lines. And so all these slopes are getting more and more negative or decreasing. That's exactly what it means for a function to be concave down. When its rate of change or its slope decreases, we say that it is concave down. So those are our more formal definitions of concavity that we'll be revisiting in calculus. But for now, I think you can get away with just thinking of it as bending upwards or bending downwards. There's a couple other definitions we have to take care of that'll help us accurately describe some of our graphs and functions that we'll be working with. And once we have those, I think it'll be a good idea, a good exercise for you to go through all the toolkit functions and describe where are our toolkit functions increasing or decreasing, where are our functions concave up and concave down, and so on. And so again, we'll go through a informal and formal definition or description of each of these concepts. So let's go ahead and start with local maxes and local mins. Those should be quick and easy to knock out. They're pretty straightforward and probably exactly what you think or expect. So a local maximum, we can just think of as a high point, and a local minimum as a low point. There are also what we call absolute or global maximums and minimums, but we'll worry about those later. We can have multiple local minimums and local maximums depending on how our function is behaving, and it is totally possible for a local minimum to actually be larger than some other area's local maximum and vice versa. And so we say our function has a local maximum wherever our function switches from increasing to decreasing. So wherever our function switches from increasing to decreasing, that is going to create a local maximum on the graph of our function. Here we can see on our little example graph down here for a concave down function, this is exactly what occurs at a local maximum, right? We clearly have a high point or a local maximum at the top of our little parabola there. Well, how do we get up to a local maximum? Well, we have to go up to it. We have to increase in order to get to that highest point. And then if it really is the highest point, right after we have hit it, we need to start going down from it. So that means right after we've finished increasing, we have to switch to decreasing. So that's our more formal definition for a local maximum. Our definition for a local minimum is very similar. We can see that in this picture here. Before our local minimum, at the bottom down here, we have to get down to it. So we have to be decreasing. And then immediately after we've obtained that minimum value, we have to start increasing. We have to actually create that value. So wherever our function f of x switches from decreasing to increasing, that switch from decreasing to increasing is going to create one of these little valleys and one of our local minimums. And so this last phrase, term, or concept is probably new to most of us, and that is an inflection point. Neither of our little graphs that I have up here at the moment have one of these inflection points. All an inflection point is, and this is our formal as well as informal definition, is it's a place where our concavity switches. And so all an inflection point is that point where the concavity of our function changes. It can change from concave up to concave down, or from concave down to concave up. I redrew those two original graphs we were looking at, or pretty close representations of them, because they are some functions with examples of inflection points. Right? In our first graph up here for this function, we are concave up until we get to about x equals 0. And then after that, we are concave down, right? If we had a straight line, had to bend it into this shape, we have to bend it up to create that shape. So we are concave up, and we can't bend a straight line to create this shape. We got to bend it down. So we are concave down here. And now we're just eyeballing and guessing at this point. We have to do that until we get to calculus. But our inflection point is just that spot on our curve where the concavity is changing. So on both these graphs, looks like it's happening right around x equals 0, but that's just a coincidence. In our second graph, here our concavity is switching in the opposite direction. First we are concave up, and then after the inflection point, we have switched to being concave down.